your hand.
Alright, so we're going to start. So I'm Mrs. Rosenbaum. I teach chemistry and physics here at Minot. Okay. For all of you who are walking in, there's a sheet on the front in case you want to have a handout. So this is going to be an introduction to particle physics. If I could teach you all of particle physics in 25 minutes, then I would not be here. But I am definitely going to give you enough that you should be able to read anything in any of the newspapers about particle physics or pick up any book about science that involves particle physics, and you should have no trouble understanding most of what's going on. And I'll give you some examples of books at the end that you could take a look at, or some articles that you could take a look at that you can use from now on. So we're doing an introduction to particle physics. So we first want to know why we're going to be studying particle physics. And the reason why is there's basically two parts. There's the pure scientists who want to know what the universe is made of, how the universe came to be, and those people don't usually care about what's going on today. It's usually far back, like what happened. And then we have the people who are the applied scientists who want to know what we can use these things for. All the things we learn from particle physics, what can we use it for? And there are examples in lots of different areas. One that I just want to point out is in medicine. This is a PET scan, PET, stands for positron emission topography. I'm not a doctor, so I can't tell you exactly what it does, but I know that it uses positrons, which are something that, a particle that we learn about from particle physics. So the particle physicists discover the positrons, and then the medical community figured out how to use it to map out parts of the brain. So what we're going to do is start with the history of how we got to particle physics today. And it starts way back as far as the Greeks and the Romans, trying to figure out what our world is made of. So one of the first descriptions of what our world was made of included air, earth, fire, and water. And they said that everything is made up of those four things. So as an example, they said that gold was a combination of earth and fire. And that's what makes the earth this shiny, almost fiery color. So they said it was a combination of those two things. And as we developed in our tools and in our thought processes, we came to discover that there actually are different elements. And this is the periodic table that we have today. It was developed starting in the 1860s, but for a while they have been discovering lots of different elements. And this is what we use in a chemistry class. There are things on here like hydrogen, oxygen, aluminum, lead. And these are the building blocks of everything else that we have. So that was in the 1860s. They're developing the periodic table. They actually announced this year they added 2 more elements to the periodic table, so we're even creating new elements. But that's what we have today to make up things like water. Water is made up of oxygen and hydrogen from the periodic table. But we weren't satisfied. We kept on going. We said, well, what is an element made of? If I have an oxygen piece, what's that smallest piece? And then they came up with the concept of an atom. And they discovered that actually atoms have parts. So we're going deeper and deeper into what matter, what stuff is made of. And starting in the late 1800s, early 1900s, they discovered the pieces of the atom. So we have protons, neutrons, and electrons, which make up the atom. And that's kind of where general chemistry in most high schools stops. We learn about the atom, the pieces of the atom, and we move on to other things. But scientists are never satisfied. They want to know, well, what makes up the neutron, the proton, and the electron? So let's get even smaller. How small can we get? What's the farthest piece we can go? And that's where we get to where particle physics is up to today, which is the standard model. And I have a copy of that on your sheet, so you can take a look at it. These are the pieces that make up the protons, the neutrons, and we'll talk about the electrons. So we're going smaller and smaller. How small can we get? So this is as small as we have today. It's called the standard model. And it shows all the pieces that we have, or that we know of, that make up everything else. So we're going to talk about what each of these things mean, how it's split up. So it's split into 2 categories. We have on this side we have the fermions. On this side we have the bosons. So we're going to start with the fermions and go to the bosons. So the fermions are called mass carriers. Which basically means that they are particles that have mass and make up other things that have mass. So everything that has mass here in this room if I go down to the ittiest little part, is going to have fermions in it. It will also have bosons for other reasons, but it's made up of fermions. Fermions are further split into two categories, quarks and leptons. Basically, the difference between a quark and a lepton is a quark can combine with other quarks to make bigger particles, and a lepton can't. So lepton is the smallest piece of itself, and you can't combine it to make a bigger piece. But a quark, we're going to combine 3 or more quarks together to make bigger particles. Now they come in pairs, up, down, charm, strange, top, bottom. Most of the stuff that you see around you is made up of up and down quarks. Those are the most common. Charm and strange, just to give you a sense, they were named in the 60s, the 70s. They had a sense of humor. There's stories about the things that they were doing while they were naming these particles, you can imagine. Top and bottom, which were discovered also like 70s, around then. Originally their names were Truth and Beauty, and then they realized they were getting too cutesy, so they said, all right, let's be scientists again, and we changed it to top and bottom. But these are the quarks, and again, we can combine these together to make larger particles. And then we have the leptons, okay, again, which we cannot combine to make larger particles. And you'll notice on this list, we have the electron. So that piece that they discovered as part of the atom here actually is the smallest of itself. And as of now, in our knowledge today, we cannot divide it any further into smaller pieces. But we're going to see that the neutron and proton are actually combinations of quarks. So you put some quarks together and you can get a proton, put some quarks together, you can get a neutron. Okay, if you take a look at the leptons, one other interesting thing about it is you'll see all these neutrinos. So neutrinos are incredibly small. Their mass is almost considered negligible, and we're talking about compared to atoms. Meaning atoms we also think of as tiny mass, but imagine tinier than that. So much so that in an article describing neutrons to like a regular person, so we have particles, around us all the time. If you take out your hand and wait 1 second, the number was 1 trillion neutrinos have just passed through your hand and did not interact with your hand in any way. Just went right through, keeps on going, goes right through the earth, through the core, keeps on going. And like the other number they said is that for the first 10 years of your life, so in a span of 10 years, only one of them might interact with one tiny part of an atom of your body. So neutrinos are incredibly small, incredibly fast, virtually undetectable. They are now building detectors to detect them, so they have a couple of them. There's one in Japan that are trying to detect these neutrinos, and they're building these massive machines, and they're detecting like handfuls of them. So they're incredibly hard to detect. And we're going to talk about how we know these particles exist in the first place. We're going to talk about how we know that. So again, quarks can combine, leptons cannot. And this is just showing you what they can combine into. So the quarks can combine to what's called a hadron. So a hadron or a hadron is when you have quarks that combine to make a larger particle. So for example, the one we're going to talk about the most they're called baryons, but if you have 3 quarks, so a proton, so that piece of the atom has 2 up quarks and 1 down, and a neutron has 2 down and 1 up. So if you combine quarks together, you can get a hadron. So those are the mass carriers, and they make up the atom, which make up the elements, which make up the desk and the chair in your body, and everything else that is in your body and the world. So now we're going to talk about these bosons. The bosons are called force carriers. Basically what that means is there are a lot of different forces in the world. There are 4 fundamental forces that make up everything in our world and connect them together or separate them. As an example of a force, right now you are being pulled towards the Earth. That's because there's something called the gravitational force. If there was no gravitational force, we would not be sitting in our desks right now. But there are actually a lot of different forces, and each of the 4 fundamental forces has what we call a boson, something that makes that force be there. So if there was no gravitational force, it's actually the Higgs boson, so that if that's not there, then there's no gravitational force. So we'll go through each of these, what they're for. So we actually learn about these forces in physics, but we don't talk about why they're there. So this is why they're there. So a photon is actually a piece of light. So whenever you see light, you're actually seeing pieces of light, you're seeing photons. So a photon, which is one of the, it's over here, listed here, sorry. So a photon, which is this one over here. So a photon is a piece of light, carries what we call the electromagnetic force. So anything that is attracted to each other because of electricity or from electrostatics, so two positive things are repelled or a positive negative thing are attracted, that's because there are photons that are making that force be there. The same thing for magnets, north side and south side magnets have that force because there are photons in there creating that force. The W and the Z bosons carry something called the weak nuclear force. Basically what it allows is it allows changes between the quarks and the leptons. So like an up can turn into a down, or a charm into a strange, or an electron into a muon. So they can change type. And they change type because of the W and the Z. We actually talk about this in chemistry, but not this way. We talk about how when you have nuclear chemistry, we can change the atoms. And we say, we have an example where a neutron turns into a proton. And we say it happens. So the way it happens is that one of the down quarks is turning into an up quark. So when it does that, we end up with, instead of a neutron, that neutron now turned into a proton. And that's by these things called the W and the Z force, the W and the Z boson. Okay, the gluon, which is another example of a force carrier, carries what's called a strong nuclear force. And that's what holds the quarks and the nuclei in a nucleus. So we said that here we have our proton, and we said we have in the proton two ups and a down. They don't really want to be next to each other. They repel each other. They don't really want to be there, so they need some sort of literally glue to hold them together, and that's called a gluon. It's a force carrier that literally sticks them together. The same thing for proton to proton. So if you look at an atom, we talk about how an atom has lots of protons in a nucleus, but the protons are positive. If you try to put two positive things next to each other, their natural state is to repel. So we say, how do they stay there? We talk about how the neutrons somehow aid in that, but really what's holding together the protons are these gluons. They literally act like glue, holding together things that normally would try to repel. And the last one, which has been in the news a lot lately, is the Higgs boson. And that's the carrier for the gravitational force. We said that there's gravity in this room. We're attracted actually to the Earth. Okay? I'm actually, right now, attracted to the desk. You are all attracted to each other. You don't feel it because it's a very small attraction, but the Earth is very large. So we feel that pull. We feel like we're being pulled to the ground. And that's carried by what's called the Higgs boson. So you are attracted to anything with mass. If you have mass, you're attracted to anything else with mass. But you feel it the most when it's a large object. So the Earth is pretty large, so we feel it, and we feel that attraction. And this is the boson that we're going to talk about a little later. This is the one that they recently confirmed its discovery. There was a Nobel Prize, so it's got a lot of press. So these are, again, the bosons. So I know I did a lot, but basically you now know what this means. The reason why there's a dotted line around this one is that this picture was made pre-confirmation. Now that they've confirmed it, I actually keep on looking and seeing, like, are they going to come up with a new version where it's not dotted, but they haven't done that yet. They're a little behind. But these are the bosons. That's basically particle physics in a nutshell. So we have the fermions. These actually are called, I didn't tell you this, they're called flavors. So like, this is the up flavor, the down flavor. Again, it's part of that 60s, 70s vibe that's going around. We have all the flavors. And we have all the pieces. So you basically know what this is and how it comes to make up other things. So the big question, and the second part of this session, is all about how do we know? How do they find these particles? We're saying they're tiny. We're saying millions and trillions of neutrinos are passing through your hand every second. How do they figure that out? So they're building a lot of detectors, and we're going to talk about the big detector that's around now, which is called CERN. So this is a particle accelerator. It basically takes particles, makes them go really, really fast, and then smashes them together. So they're kind of like kids. They're like, let's see how fast we can go, and let's see how many big explosions we can make. So the biggest one, I'm going to turn the lights off so you can see this better. better. The biggest one is in CERN. It's actually at the border between France and Switzerland. To give you a sense of scale, these are the, I can't remember if it's the French Alps or the Swiss Alps. It's one or the other, it's the mountains. This is the snow on the top. These are cities, that's a big, big lake. And this is showing you kind of an overlay of where the machine is underground. So this is underground, underneath all this farmland and pastures. Don't worry, they got signatures from these people to make sure they can build it there. They've been building it since the 1980s, and they finished building it in around 2008. That's when they started it up to its full capacity. And the main goal of this is to prove and to advance our understanding of the particle physics, of understanding that big chart that we just saw. So if you take a look, I think you have this picture. Okay, so this is, I gave you this one. All this, by the way, comes from, CERN is very open about their information. They put a lot of stuff on their website. Anytime they have discoveries or animations, they just stick it all up there for everyone to see. So they're, so it's like a list of 30-something countries. You can look online about the total list, but it's about 30 countries work together on this, including the United States. A lot of our National Science Foundation, NSF money, and a lot of our other money from our government is used in this machine. So these are just the stats. It's 330 feet underground, 16.7 mile circumference. That's like if you were to walk around the circle, that's how long it would be. The inside, not where the people are, but the inside of the machine is colder than outer space. And it involves 9,300 magnets, and I'm not talking about little magnets that you put on a fridge. I'm talking about magnets that could be the size of this room or the size of this building. So this is a huge operation. I'm sure you can look up online how many billions of dollars it took just to build this and how much money it took to run it takes to run this. So much so that they close in the winter to save on energy costs. So they don't run, they're actually closed right now. They do repairs and stuff in the winter so that they don't have to pay the premium cost on electricity. Because you can imagine there's a lot of electricity that they're using. So this is the main detector, the main ring, and there are 4 detectors that they use to do their actual discoveries. There's ALICE, CMS, ATLAS, and what's called the LHCb. Those are the 4 detectors. So this is how it works, and I have an animation for this also. This ring over here is the insertion ring. So there they put particles into this large beam, this large circle. They're going to go around 2 beams in opposite directions, swirling around. And what their goal is to have those 2 beams come together and hit and make a little explosion called an event inside the detector. So they're running around, they get to the detector, bam, explosion. Keep on going, get into the detector, bam, explosion. They're going almost as fast as the speed of light. I'm trying to remember, I looked up, there was like a number, like how many times it's over here, 600, there are 600 million collisions per second inside the detectors. So they're very fast, a lot of data. What they're running through there are hadron bunches. And if you didn't catch this, a hadron is when you have quarks combined to make a larger quark. Basically, the hadrons are dealing with our protons. So they're taking protons, circling them around really fast, and having them literally collide. Each bunch has 115 billion protons. And to give you a sense of scale, if you take a hair and you cut it 11 centimeters long, that hair is about as big as the beam is. 115 billion protons going around that fast, this is the strand of a hair. So it's this tiny little beam, and they're circling around and having it collide inside a detector. And right now, they were running at a lower amount of energy until now, and one of the big repairs that they're doing for the next 3 years, so in about 2015, they're trying to get it to the maximum energy that they can get it to. So the machine was built for a certain amount of energy, but they've been running it at a lower energy, making sure everything works. And now, over the next few years, they're going to adjust it and repair it and make it go at an even higher energy. One thing I just want to point out, they started running it in 2008. It was around the time that I came here at my note. And there was a lot of skepticism. They've been building the machine for 20 years. Like, is it going to run on the first day? And it basically went off without a hitch. So you can imagine, like, we do 100 million things a day and a year that don't go well, and they're so simple. This is a very complicated machine, but it basically, they started running it, and it was good to go. There were very few complications in the beginning and very few complications now. Yeah?
wanted to ask, where do they get where do they get the particles? I mean, what are
So
they?
the insertion beam is where they take larger things, like larger atoms and elements. So we have it in the lab. You can buy compounds and stuff like that. And the insertion beam is where they weed it out. So how they do that is a very complicated process of, it's kind of like sieving. They're like taking out smaller and smaller until they get to a proton bunch. So like the technical of each piece is obviously very complicated, but that's what they're doing over here. Here they're kind of making it into the beam, and then once they got the good beam, then they insert it, and it goes around. And then when they need a new beam, they make a new one. So that's what this little white one is where they make the original beam, and it's by a process of kind of like elimination. They're like making it thinner and thinner and smaller until they get what they want.
Why just protons and not neutrons or electrons?
So protons are the one that, so why they chose protons versus neutrons, I don't know. I think it has to do with the fact that it's charged. Protons are charged, so they need something that's going to react to the magnets. They also do lead sometimes for other experiments. They'll put lead atoms in there and circle them around. I'm pretty sure they have to be charged lead atoms, like they have to be ones that are positively charged, otherwise they won't circle. Neutrons won't react to magnets. Neutrons would just go straight. They do have straight in one of the first particle accelerators is called SLAC. It's in Stanford, in California, and they did a lot of the initial experiments on this, and that's a linear accelerator, so there I think they can do neutrons. But here it's circular, so they need the protons. Yeah.
And what are they looking to observe at these explosions? Like
good. So that's this. So this is what are they looking for? So they're making an explosion. Sounds like a bunch of kids playing. The question is, what are they trying to do? So what they're looking for is what we call an event. So I'll turn the lights off so you can see this. So this is an animation. What you're going to see is it's hard to see, but there's like a dark red. That's like the detector. And there's this little blue thing coming on this side, and when it zooms in, you'll see another blue one coming the other side. Those are the proton bunches. So we have these thin, literally strands of hair, protons, coming at each other, and you'll see what happens when they hit. So they're coming in. So one from either side, bam, and look what they get. A nice big spray of particles. So what they're looking for is they're looking for those protons to hit. The better they hit, the more spray that we get, and they're going to analyze that spray and see, okay, we hit protons and protons, what came out of that? Did we get smaller particles? Did we get bosons? Did we get fermions? Did we get things we expected? Did they get things that we can't expect, like that we couldn't account for? Mm-hmm. So that's called an event. Every time there's a collision, so just remember there are 600 million of these per second when they're running the machine. So you can imagine that's a lot of data. So some of it is, it's sent to this computer, these big supercomputers. Most of them are just cataloged as not really so important based on the way it looks. But sometimes they'll get one that looks interesting, and the computer will tag it, and then the scientists will go and start analyzing it. Remember, there are 30 countries. I think it was something like 1,000 scientists from America who are there, I don't know about full-time, but that's their job, that's their work. They each have a bunch of graduate students, and that's just America. So we have thousands, probably tens of thousands of scientist graduate students who what they do for their PhDs or for just their job is analyze stuff like this. So this is what they're looking for, and now we're going to see how they analyze it. So the way that they analyze it is they put it through this detector. So that's a picture. I'll turn the light off so you can see this. This is a picture of the detector. That little white dot is a person's hat. So these detectors are huge. And this actually is a small one. It's called the compact muon solenoid. Compact because it's relative to the other ones. It's small. So what's interesting is we're looking for tiny things, and the only way to find them is with very, very large machines. So you can imagine if we try to go beyond the standard model, like beyond this, and see if there's even smaller things, the machines are just going to get bigger and bigger. So this is the small one. This is one of 4. And basically the way it works is as follows. It detects it through layers. So here, this circle here, I gave you this picture. This circle here is where the collision happens. And the collision happens, you get the spray of particles. And these spray of particles are going to try to go through all of these detectors as far as they can. And depending on what it is, will determine how far it goes. So for example, this red section over here is the muon detector. So if you press the muon, so the muon goes through all the other parts in the middle, but it's going to make marks, see how it's going to make marks here. So that's how they know that this thing is a muon, because it made like detector detected it at this point. And if you notice it curved, that's because a muon is charged. So a muon is going to curve because we have some magnets in there. If you put an electron is going to stop over here because this is the electromagnetic calorimeter. You don't have to know each piece, but it's going to stop here. And an electron also curves because it's charged. If you put a neutral hadron, so that's going to go over here to the hadron calorimeter. So this track is going to stop here. It was neutral, so it's going to be straight. Charged hadron is going to stop at the same place, but it's charged, so it curves. And a photon is also going to stop at the electromagnetic calorimeter, but it's going to be straight because it's not charged. So the point is that they have all these layers, and each layer detects a different thing, and then they can analyze each of those individual tracks. So they analyze each track, and then they try to figure out where those tracks came from. So that's, I gave you this picture. This is an example. This is a real experiment that they did. You can read, this is from 2010. Here's the date. It tells you which run and which event this is. They have a lot of these other websites, so you can look up a bunch of them. And this is an interesting one because here we have all the tracks. They're going to analyze them, see what each piece is. But what you see here is we have these two jets, which basically is a large energy deposit. So that means something interesting happens here. Two things hit in a way that it released an incredible amount of energy. So they're going to go back, and again, this part they'll have to take a much longer course for, but they're going to go back and try to figure out, well, where did that energy come from? Was it from a new fermion? Was it from a boson? Like, what did it come from? And that's where all the math analysis comes from, but that's what they're looking for. And they analyze hundreds of these probably in a day, because they have all these people working on them. That's what they're doing, is they're analyzing these and looking for interesting things. If it's not interesting, they have the computer do it, and then maybe later they'll look at it later if they just want to check. But anything interesting like this, it's going to be flagged, and they're going to have their scientists check it out. And they were looking for a lot of things here, but the big thing that they were looking for was the Higgs boson. So they're looking for this Higgs boson, which is which one? Which one on our list?
Gravitational force.
Good, the gravitational force. So this is the one for the gravitational force. Why are we attracted to objects that have mass? Why is there gravity? And actually, when I teach my students about gravity, and the student says, well, why? I say, that's a really good question. It's actually very complicated. And it has to do with this Higgs boson. It's named for a guy named Peter Higgs. He was one of the two scientists that proposed this in the 60s, 70s. I don't remember the exact date. It's been called the God particle. It has nothing to do with, everything has to do with God. But it has nothing specifically to do with God. If you actually read the guy who wrote the God particle, the book about this topic, he actually wanted to call it the goddamn particle because it was so hard to find, and they couldn't find it. And if they couldn't find it, then this whole model that we just described would be nil, nothing. They'd have to start from scratch. So it was like, we better find this or we're in trouble. But the publisher basically said, we're not calling it that, so they changed it to the God particle. But the name stuck, so like all like the New York Times, all like the colloquial non-science kind of stuck onto it. And the scientists initially hated it. They were like angry about it, but then they realized it was actually giving them a lot of press that they might not have normally had. It made it very popular, so they kind of got excited about getting, for once, they were popular. So basically they were looking for it. You can read what they were looking for, but they were looking for it. And then in last year, July 4th, 2012, the CMS, the detector that we did, basically announced, based on the data that we have found the particles that come from the Higgs, meaning that they say it exists. One of the other ones, I can't remember if it was Atlas or Alice, one of the other detectors recently published their data saying, we also have confirmed its existence. It does, based on what we see, it exists. And then this year, they announced that the physics Nobel Prize was going to both Peter Higgs and also to Francois Englert, who at the same time as Higgs made the discovery, or made the theory. One of the interesting things about Nobel Prizes in science, the people at CMS have been doing 30 years of work to find this thing. Obviously they get credit in the world, but there's no prize for the people who found it. The prize goes to the person who thought of it. So they thought of it, so they get the prize, and the other people, obviously they were very excited. If you watch online, you can find like where they announced it. So like all the people from CERN were kind of hanging out, and you could see them drinking and like getting excited, and then they announced it, and they're all cheering and excited. But obviously they're not getting the, I think it's $1.5 million prize, or I guess it's split, so it's like $600,000 prize. But obviously they're excited for it, but there's no prize for the experimentalists who found it. So that's where we are today. So at this point today, in the general science world, this is where we're at. You know, come back in 50 years and maybe we'll have, wait, the quark is actually made of something else, and we'll find a smaller piece. But this is where we're at today. And I just want to give you some take home. So just a few things for you. On the bottom of your page, you have some books that relate to either science in general or to specifically particle physics. Some of them are more biology. They're not all necessarily particle physics, but they're all related to science. I put them in order of meant for people with less science background to meant for people with more science background. But there are pieces of all of them that you can read. They're not the same. These are just my sources. Just some websites if you want. The CERN website, you just look up CERN, you'll find it. Fermi was a lab that was in Chicago. It's actually recently closed, but they still have a website with some stuff on it. Hyperphysics, Particle Inventor is very good, specifically related to particle physics. And the New York Times. So the New York Times actually has some really cool stuff. I actually get very mad at the New York Times because the Science Times is always about health and biology, and I am not a health or biology person at all. So whenever they have chemistry or physics, I get really excited. So their section, if you go into New York Times and type in Higgs Boson or CERN or anything like that, they actually have a lot of really cool animations. An article somewhere. So this is one of their animations that basically says everything I said with some cool animations. And they also have the picture that I gave you there. There's like this little cartoon. So that cartoon was actually from the New York Times. Last year they had an entire science section that was all about the Higgs boson. And I was like, yes, like this is my day. So they had, it's called the What is the Higgs interactive graphic. So they had this in that newspaper, but then they created it into like an interactive graphic. So it talks about what is the Higgs, how do we discover it, and that's so I printed it for you. But you can also go online and see the interactive aspect of that. So I know this was a lot, but I hope that you now feel confident to either read more science, or if you see anything about the Higgs boson, you'll say, I can read through this, I can do it. And now, you know, at your Shabbos table, you have some very interesting things to tell people. Right. Want to turn? Yeah.
When they're looking for a new particle, and they know it doesn't know it's straight, so how do they build a filter to detect it?
Right. So what happens is they have the theorists who predict that the particle